Okay, in this class I just want to look at another example of Newton's laws and angles. This time where the plane, the actual plane, is inclined at an angle. Okay, so the plane is inclined at an angle. So again, if we think about the forces acting on, well, actually before I think about any forces, if I just think about the angle, suppose this plane is inclined at an angle of, let's just say, A degrees above the horizontal. Okay, one thing to kind of note here, uh, well, actually we'll come back to that in a second. If I want to think about the forces on this particle, I'm going to ignore any friction. Let's just say it's smooth. Okay, there's going to be the weight of the particle. Remember, the weight of the particle is always acting directly downwards. Notice that is not perpendicular to the plane in this case. So that's going to be the weight of the particle. That's going to be the weight of the particle. The weight is the force on the particle by gravity. That's the weight of the particle. Also, there's going to be a normal reaction. Notice the normal reaction in this case is not going to be vertical. It's a contact force, so it's normal to the plane. There's the plane, so it's going to be kind of out that direction. Let me try that again. That's not. So it's going to be perpendicular to the plane, heading out that direction. Okay? And if we're talking about a smooth surface, these are really the only two forces at work here. Okay, so if I want to investigate the motion of the plane, what I've got to be able to do is resolve this weight force, this weight vector, so that it can be perpendicular to the plane and parallel to the plane. That's what I want to do. Make a little right triangle. So I want to think about these angles a little bit. Ultimately, I want to think particularly about this angle in here. So to think about that angle in there, if I kind of imagine, extending this out here and make that a little right angle, this is A, which means this angle here would be 90 minus A, which means this angle in here would have to be A. Okay, that has to be A, and that's something you need to think about and get into your head. You need to be able to kind of figure that out. So working out from there, going through my components of my weight vector here, W is the hypotenuse. This component over here adjacent to the angle will be W cosine the angle A, and this over here, the opposite, will be W sine of the angle A. And before you try any question on a particle sliding down the inclined plane, you should be able to do this kind of stuff. The other thing, if I said, instead of saying it was smooth, suppose I said it was rough, well, what way is friction going to act? Well, friction opposes intended motion. So this is intending to slide down the hill. So any friction force would be acting parallel to the plane back up the hill. Okay, and I want to look at two examples of that. And particularly I want to look at on smooth surfaces. So get used to resolving. You're going to be doing it a lot. So here I have a 10 kilogram particle sitting on a plane. I want to think about the forces at work on that particle, and there are various forces at work. The first force that I always think about is the weight force, which is acting directly towards the center of the earth. That's the weight force. It's acting down. Remember, the weight is the force on the object by gravity. Okay? And the weight of any force is its mass times little g. Okay, if I assume g is 9.8, the mass here is going to be 98. Okay, or 10g is probably the simplest way to think about that. Okay, also the other force at work here is going to be the normal reaction, which is going to be perpendicular to the plane, kind of heading out in this direction. Okay, there's my normal reaction. I'm just going to call that or for the moment. There are no other forces at work on this particle. If it's just placed on the plane, it's just sitting there, no other forces. Notice I've said that I want this to be smooth, which means friction is not acting. It's not a driving particle, it's just something that is sitting there. So what I'm always going to want to do is resolve my weight vector here to be perpendicular and parallel to that plane. That's what I want to be able to do. And using a bit of geometry, if that's 30, well, that must be 60 in here, which means this must be 30 up here. And as you get used to practicing this, you'll just end up writing 30 in here. Special triangle, that's a useful thing. If I don't know my special triangles, we've got to know that the opposite in a right triangle is always the hypotenuse times sine of the angle, and the adjacent is always the hypotenuse times cosine of the angle. But I should know my special angles, and in the right triangle 30, 60, 90, the side opposite 30 is always half the hypotenuse, so that's going to be 49. And the side opposite the 60-degree angle over here is always the side opposite 30 multiplied by root 3. So now we have the forces at work. Again, it's a particle on a plane. This is a plane. This green thing is a plane. You know, a plane surface. Maybe it's a hill or something like that, or a snowy mountainside, something like that. So I want to think about the force is perpendicular to the plane first of all. Well, it's not going to be accelerating into the plane or away from the plane. It's just going to slide along parallel to plane, which means the up forces are equal to the down forces. I apologize for writing FU in here, but that just means the force is up. So the force up or is going to equal to the down force here, in this case 49 root 3. Now that would be important if we were dealing with friction, but because it's a smooth surface, it's not really a big deal. The other kind of forces I want to deal with are going to be my parallel forces. So parallel to plane, there's only one force in town, and this is this force. It's 49. This is going to be pushed or pulled down the plane with a force of 49 newtons. We're using F equals ma here. Of course, F net, the net force equals mass times acceleration. The only force at work is this 49 Newton force pulling it along parallel to the plane. So we get 49 is equal to the mass of this thing, which is 10, multiplied by its acceleration. So what are we getting? Its acceleration is going to be 4.9 meters per second squared. Okay, so on a smooth surface. Fairly straightforward. Okay, only two forces at work on the particle. The weight pulling it down towards the center of the Earth, not perpendicular to the plane in this case, and the normal reaction. Not vertical in this case, but rather perpendicular to the plane. You've got to remember those things. From there, resolving my weight vector and examining forces perpendicular and parallel to the plane shows me the acceleration is equal to 4.9 meters per second squared. I want to look at this very similar example, but I just want to see if I double the weight of the particle, what happens, you know, and have a think about what happens. Do you think it'll accelerate at a higher rate than 4.9 meters per second squared, or at a slower rate? If it's heavier, maybe it'll move slower, or the same rate. You know, think about those things before you go and answer it. I'm going to go through, you know, the whole thing. So we have my weight vector going that direction. I've got my normal reaction there. Sorry, wrong thing there. I've got my normal reaction perpendicular to the plane, like so, something like that. And I'm just going to call that or in this case. Notice the weight of the object has increased, so you would imagine the normal reaction would be bigger in this case as well. This is my weight vector acting down towards the center of the Earth. Remember, weight is always mass times little g. I'm going to just give little g the value 9.8. So 20 times 9.8 will be 196. So that's my weight force here. The weight of this object is 196 newtons. We go and resolve this to be perpendicular and parallel to the plane. If this is 30, well then this is 30. It's a 30, 60, 90. The side opposite 30 is always half the hypotenuse. That means that's 98 newtons. And the side opposite 60 is always root 3 times the side opposite 30. Special triangle. If you're unsure about that, just the side opposite is always the hypotenuse times sine. Side adjacent is always the hypotenuse times cosine. Just like we did before, I'm going to look first of all at the perpendicular forces. And again, the forces up are going to equal the forces down, because this particle is going to just slide along this plane. It's not sinking into the plane or rising away from the plane. So we can get that the normal reaction in this case will be 98 root 3. So the normal reaction, what has happened there? The difference, but it's double the last one, right? It's double the last one. What about how to install updates? Apologies now. Let's get rid of that. And now I'm going to look at parallel to the plane using F net equals ma, Newton's second law. In the perpendicular case, there was no net force. Forces up equal force down. Here, the net force, well, parallel to the plane, the only force pulling down the plane is this 98 Newton force, which is pulling the object down towards along the plane. So that's my only force. So the net force here is 98. And that's equal to the mass, which is 20 times A. Solving there, the acceleration is going to be 98 divided by 20, which is going to be 4.9 meters per second squared, which is exactly the same as when we had a 10 kilogram object in here. Okay, the acceleration is the same. And it can be shown for any object of any mass sliding down here, if it's a smooth surface, the acceleration will always be the same. Let me just take m to be just m's for any mass m. Let's prove this. Weight acting downwards, which will be mg. Normal reaction acting perpendicular to the plane, which is going to be r. Resolving my weight vector. That's 30. Remember, the side opposite 30 is always half the hypotenuse, and the side adjacent to 30 is always the side opposite 30 times root 3. Okay, I can look at the perpendicular forces. It's smooth though, so I'm not even going to bother in this case. I'm just going to skip straight to the parallel forces. Remember, we said F net is equal to ma. Parallel to the plane, the only force parallel to the plane is this mg over 2. So I'm getting mg over 2 as my net force parallel to the plane. That's equal to the mass, which is m, times the acceleration, which we have to find. Okay? Dividing there on both sides by m, I'll just squeeze it in over here. Dividing on both sides by m, I'll get g over 2 is equal to a, which means that a is a half of g, which is 4.9 meters per second squared. So one thing to note, the acceleration of the particle does not depend on the mass of the particle at all. What it does depend on is the angle that the plane is inclined, okay, and it would also of course depend on whether it's smooth or rough, and how great friction is. But the mass of the object isn't really affecting the acceleration in this case. Any mass placed on a smooth surface inclined at 30 degrees is going to accelerate at 4.9 meters per second squared. Okay, whether it weighs the same as a tractor or whether it weighs the same as a shoe, it's going to accelerate at the same rate, assuming the surface is smooth, okay, and ignoring things like air resistance. Alright, so have a think about that, and I'll look at my next class at introducing a bit of friction and seeing how that changes things up on an inclined plane.